Let us view the different types of linear programming problems with the help of few important applications. Like in manufacturing problems. In such problems, we determine the number of units of different products which should be produced and sold by a firm, where each product is subjected to different constraints like fixed manpower, machine hours, labor hour per unit of product, warehouse space per unit of the output, etc., in order to make maximum profit. The other application of linear programming problem is in diet problems. In these problems, we determine the amount of different kinds of constituents or nutrients which should be included in a diet so as to minimize the cost of the desired diet such that it contains a certain minimum amount of each constituent or nutrients. Similarly, the linear programming problem can also be applied to transportation problems. In these problems, we determine a transportation schedule in order to find the cheapest way of transporting a product from plants or factories situated at different locations to different markets. Let us now consider a manufacturing problem as follows. A bicycle company produces two kinds of bicycles, mountain bikes and street racers. The company wishes to determine the rate at which each type of bike should be produced in order to maximize the profits on the sales of the bikes. The company assumes that it can sell all the bikes produced. A different team produces each type of bike, and each team has a different maximum production rate. 2 mountain bikes per day and 3 racers per day, respectively. Producing a bike of either type requires the same amount of time on metal finishing machine, and this machine can process at most a total of 4 bikes per day of either type. Mountain bikes are currently generating a profit of around 15 rupees per bike, and racers a profit of around 10 rupees per bike. Now, we formulate and solve this problem as a linear programming problem. The first step in formulating the bike problem is to identify the variables. These variables are the items whose values can be set or otherwise controlled. The variables are, in fact, the production rates of the bikes. Let these variables be X and Y for the mountain bikes and the racers respectively. Note that if there is any bounce on the variables, then we get a non-negative constraint. X is greater than equal to 0, Y greater than equal to 0. Now, using these variables, we can write the objective function as follows. Maximize Z equals to 15x plus 10y, where maximize daily profit equals to Z. Further, we use the variables to write the constraints as well. X less than equals to 2 mountain bikes per day. Also, Y less than equals to 3 racers per day. Also, we know that the metal finishing machine production limit is 4 bikes per day. Therefore, we get one more constraint as X plus Y less than equals to 4. As there are only 2 variables in the problem formulation, the problem can be sketched on the plane as shown here. Note that the limiting value of each of the constraints is shown as a line, while points in the feasible region, including the boundary lines, satisfy all the constraints. Thus, the linear programming problem in the figure is to find the point in the feasible region that gives the largest value of the objective function. As shown here, points having the same value of Z, value of the objective function, form a line. This is easy to understand by replacing z by the specific value that we want to plot. For example, z equals to 15x plus 10y becomes the line 15x plus 10y equals to 15 as shown being plotted in the figure. The figure also shows that all of the constant profit lines are parallel. This is because all the constant profit line equations differ only by the selected value of z. All the constant profit lines have the same slope, -3/2 as shown. Now the linear programming question is, what is the last point in the feasible region through which the objective function passes when moving upwards? Note that the last point is 2, 2, which gives the value of z as 50. This is actually the solution to the linear programming problem. Thus the point 2, 2 is the feasible point that has the best value of the objective function. Let us now consider a diet problem as follows. Once, Bully found that the weighing machine broke down because he was overweight. His mother advised him to go on a diet. Since Bully needs iron and a limited amount of fat, he was restricted to food A and B. Food A provides 2 units of iron and 2 units of fat. Food B provides 1 unit of iron and 2 units of fat. He must get at least 80 units of iron and, at most, 100 units of fat daily. Represent the inequalities mathematically and graphically. First, let us make a table showing the types of food and the amount of nutrients it provides. Food A provides 2 units of iron and 2 units of fat, whereas Food B provides 1 unit of iron and 2 units of fat. Suppose Bully takes X units of food A and Y units of food B daily. It is obvious that Bully cannot take in negative amounts of food A or B. They can either be positive or be equal to 0. Thus, we get first 2 inequalities. X is greater than or equal to 0 and Y is greater than or equal to 0. Label these inequalities as 1 and 2. Now, the amount of iron is greater than or equal to 80. This is because Bully must get at least 80 units of iron. From the table, we know that each unit of A gives 2 units of iron. Thus, X units of A have 2x units of iron. Similarly, each unit of B gives 1 unit of iron. Thus, Y units of B have Y units of iron. Therefore, 2x plus Y is greater than or equal to 80. Note that the obtained inequality is not in the standard form Y is equal to mx plus c. We rearranged the terms of the inequality to get Y is greater than or equal to minus 2x plus 80. This gives us our third inequality. Further, Bully can take at most 100 units of fat daily. Therefore, amount of fat is less than or equal to 100. Again, from the table we know that each unit of A gives 2 units of fat. Thus, X units of A can give 2x units of fat. Therefore, 2x plus 2y is less than or equal to 100. Again, this inequality is not yet in the standard form. Y is equal to mx plus c. So we rearrange the terms, and by dividing both sides by 2, we get equation 4 as shown. Thus, we have obtained the 4 inequalities. Let us plot them on a graph. On the graph, we have 2 axes, x and y. Observe that the scale of the graph is also shown in the right corner. Let us plot the first inequality, which is x is greater than or equal to 0. To plot the first inequality, we need to plot the line x is equal to 0. This line is nothing but the y-axis and forms the boundary for the first inequality. Now to determine the region, we need to check the sign of the inequality. Here, the sign of the inequality is greater than. Thus, the required region would lie to the right of the boundary. But note that there is also an equal sign in the inequality. Thus, the line itself is also included, and we do not show it as dotted. Now, let us plot the second inequality. To plot this inequality, we need to plot the line y is equal to 0. This line is nothing but the x-axis and forms the boundary for the second inequality. To determine the region, we need to check the sign of the inequality. The required region is above the boundary because the inequality has a greater than sign. Also, the line will be a part of the required region because there is an equal to sign too. So, we do not show the line as dotted. Let us plot the third inequality. Y is greater than or equal to minus 2x plus 80. To plot the third inequality, we need to plot the line y is equal to minus 2x plus 80. To determine the region, we need to check the sign of the inequality. Here, the sign is greater than in the inequality. Thus, the required region would lie to the right of the boundary. Note that there is also an equal to sign in the inequality. Thus, the line itself is also included, and we do not show it as dotted. Now, to test whether the required region is correct or not, let us choose a point at random, say 0, 0. It is clearly seen that the chosen point lies outside the region. On the left-hand side, we have 0, 0 equal to y, which is equal to 0. But we need to see that mathematically by checking whether the selected point satisfies the third inequality or not. Note that the chosen point 0, 0 does not satisfy the inequality as shown. Therefore, the required region is correct. Let us plot the fourth and final inequality. To plot the fourth inequality, we need to plot the line y is equal to minus x plus 50. To determine the region, we need to check the sign of the inequality. Here, the sign is less than in the inequality. Thus, the required region would lie below the boundary. Note that there is also an equal to sign in the inequality. Thus, the line itself is also included, and we do not show it as dotted. To test whether the required region is correct or not, let us choose a point at random, say 0, 0. It is clearly seen that the chosen point lies inside the region. But we need to check that mathematically by substituting the selected point in the fourth inequality. Note that the chosen point 0, 0 does not satisfy the inequality as shown. Therefore, the required region is correct. Thus, all the 4 inequalities are plotted on the graph. Let us observe all of them together and find the overlapping region. Note that the overlapping region is a triangle, which is in fact the feasible region. Let us solve some more examples. Example: A cement manufacturer has two depots, D1 and D2, which contain current stocks of 80 tons and 20 tons of cement respectively. Two customers, C1 and C2, place orders for 50 and 30 tons respectively. The transport cost is 1 rupee per ton per kilometer, where the distances between depots and customers in kilometers are given in the table as shown. Now, from which depots should the orders be dispatched in order to minimize the transport cost? Suppose the depot D1 distributes X tons to customer C1 and Y tons to customer C2. Then, depot D2 must distribute 50 minus X tons to customer C1 and 30 minus Y tons to customer C2. All quantities are positive and the following inequalities must be satisfied. The total cost of transport, T, are made up of 40x, 30y, 10 into 50 minus x, and 20 into 30 minus y, as shown in the table. Therefore, we get the objective function as shown. In fact, this objective function has to be minimized. Let us now plot the graph for the obtained inequalities as shown, and find the feasible region. From what we have learnt till now, we need to evaluate the objective function at the points 30, 30, 50, 30, and 50, 10. Hence, we find the values at these points as shown. Note that the minimum cost occurs at the point 30, 30, so that depot D1 should send 30 tons to customer C1 and 30 tons to customer C2, while depot D2 should send 20 tons to customer C1 and 0 tons to C2. A dietitian has to develop a special diet using two foods, P and Q. The content in each packet of food, P and Q, is shown in the table. The diet requires at least 240 units of calcium, at least 460 units of iron, and at most 300 units of cholesterol. How many packets of food P and Q should be used to minimize the amount of vitamin A in the diet? What is the minimum amount of vitamin A? Let X and Y be the number of packets of food P and Q respectively. Obviously, variables X and Y are greater than equal to 0. Mathematical formulation of the given problem is as follows. If Z is minimum amount of vitamin A, then the objective function is to minimize Z equals to 7x plus 2y. From the table we get the following constraints. Calcium, 4x plus y greater than equals to 80 as shown in equation 1. Iron, x plus 5y greater than equals to 115 as shown in equation 2. Cholesterol, 3x plus 2y less than equals to 150 as shown in equation 3. And we already know that the variables x and y are greater than equal to 0. We will make the graph of all these inequalities as shown. Note that the shaded feasible region determined by the constraints is bounded as shown in the figure. The coordinates of the corner points L, M and N are as shown in the table. Let us evaluate Z at these points as shown. Hence, the amount of vitamin A under the constraints given in the problem will be minimal if 15 packets of food P and 20 packets of food Q are used in the special diet. The minimum amount of vitamin A will be 145 units. A manufacturer has 3 machines installed in his factory. The first and second machines are capable of being operated at the most for 12 hours, whereas third machine must be operated for at least 4 hours a day. She produces only 2 items, M and N, such that each requires the use of all the 3 machines. The number of hours required for producing 1 unit of each of M and N on the 3 machines are given in the table as shown. She makes a profit of 700 rupees and 300 rupees on items M and N respectively. How many of each item should she produce so as to maximize her profit, assuming that she can sell all the items that she has produced? What will be the maximum profit? Let X and Y be the number of items M and N respectively. Total profit on the production equals to 700x plus 300y rupees. Mathematical formulation of the given problem is as follows. Maximize Z equals to 700x plus 300y, subjected to the constraints. Machine 1, x plus 2y less than equals to 12. Machine 2, 2x plus y less than equals to 12. Machine 3, x plus y greater than equals to 4. Let us plot the constraints on the graph as shown. Note that the shaded region A, B, C, D, E, as shown in the figure, is the feasible region determined by the constraints. Observe that the feasible region is bounded and the coordinates of the corner points A, B, C, D and E are as shown in the table. Let us evaluate the value of Z at these corner points. Observe that at the corner point B, 6, 0, the value of Z is maximum. Hence, the manufacturer has to produce 6 units of A to get the maximum profit of 4,200 rupees. There are 2 factories. One of them is located at the place P and the other at the place Q. From these locations, a certain commodity is to be delivered to each of the 3 depots situated at A, B and C. The weekly requirements of the depots are 5, 5 and 4 units of the commodity respectively, while the production capacity of the factories at P and Q are 8 and 6 units respectively. The cost of transportation per unit is given below. How many units should be transported from each factory to each depot in order that the transportation cost is minimal? What will be the minimum transportation cost? The problem can be explained through a diagram as shown. Let X units and Y units of the commodity be transported from the factory at the place P to the depots at A and B respectively. Then 8 minus X minus Y units will be transported to depot at C. So, we have variables x and y, and 8 minus x minus y are greater than equals to 0, or x greater than equals to 0, y greater than equals to 0, and x plus y less than equals to 8. Now, the weekly requirement of the depot at A is 5 units of the commodity. Since X units are transported from the factory at P, the remaining 5 minus X units need to be transported from the factory at Q. Obviously, 5 minus X greater than equals to 0. That is, X less than equals to 5. Similarly, 5 minus Y, X plus Y minus 4 units are to be transported from the factory at Q to the depots at B and C respectively. Thus, 5 minus Y greater than equals to 0. X plus Y minus 4 greater than equals to 0. Or Y less than equals to 5, X plus Y greater than equals to 4. Hence, the total transportation cost, Z, is as shown. Therefore, the problem reduces to minimize Z equals to 10 times 4x minus 8y plus 168, subject to constraints as shown in inequalities 1, 2, 3, 4 and 5. Let us now plot the constraints 1 to 5 on the graph as shown. Note that the shaded region A, B, C, D, E, F represented by the constraints 1 to 5 is the feasible region. Observe that the feasible region is bounded. And the coordinates of the corner points of the feasible region are A, B, C, D, E and F as shown in the table. Let us evaluate the value of Z at these points as shown. From the table we see that the minimum value of Z is 1280 at the point B. Hence, the optimal transportation strategy is as shown in the table. Corresponding to this strategy, the minimum transportation cost is 1280